Okay, thank you, John. Thank you all for coming. I entitled my talk, What's My Line?, after a television show I used to watch when I was a kid. I don't know how many people remember that show. A guest would come on, they would have sort of a unique profession, and they would walk in and sign in, and then there was a panel of, I guess I'd call them semi-famous people, who would be able to ask questions of this guest, and after asking questions would try and figure out what their profession was or what their line of work was, thus the name What's My Line? So I don't know if you recognize this picture. It was on the flyer. Okay, so this guy would have been a great guest. His name's Svante Arrhenius. We'll talk about him later, but had he been on the show, he would have walked in, signed his name, and then the panel would have asked him questions and trying to figure out what did he do for a living, what was his line of work. Okay? And so I thought that was a good analogy for what my talk is going to be about, because we're going to talk about lines too. We're going to try and figure out how scientists process their data to find linear relationships between their variables. So I'm going to show you some data from experiments and see how when the data is first measured, you don't necessarily have a nice linear relationship, but how the chemists go through and manipulate it mathematically, not doing any cheating or not too much cheating, but manipulate it mathematically in order to get it into the slope-intercept form, because chemists like to look at things in the slope-intercept form. We have very simple minds here. So that's what we're going to go with. So our first set of data, this was actually obtained 2 weeks ago by some students in my Chem 110 lab. Okay? And I'm starting out with a nice simple set here. And I'm going to sort of run this in that I want you to look at it and see if you can figure out what the relationship is between your x variable and your y variable. See if there's some kind of relationship. Is it linear? Okay, is it logarithmic? Okay. Is it inverse, the inverse relationship? And then I'll go through the manipulations and we'll see if we can figure out how to get it into the slope-intercept form. So I actually put the numbers here that they measured. I didn't tell you what they measured. I'll let you see that. It might help. Okay. They were measuring pressure in bar, units of bar, versus temperature in Kelvin. Okay. Anyone recognize that relationship? Okay. Okay. It's a famous equation determined in the early 1800s. If I look at those lines, or those data points, I actually think they're pretty close to being linear. If I put my fit in there, that's the best fit that the computer will give me. And this turns out to be what's called Gauss Law. Okay. It was determined in the early 1800s. French physicist, and the relationship is the pressure equals a constant times the temperature. So there's a nice linear relationship. Chemists love these kind of relationships. Nice and easy. You plot the data and you realize, oh, when I first plotted, I have perfect y equals mx plus b form. I can figure out that my constant's just going to be that slope of the line. Okay? So this seems kind of straightforward, but it was done, as I said, in the early 1800s. The equipment that they used in the early 1800s wasn't quite as sophisticated as ours, so even though the determination of that line was easy, actually the gathering of the data wasn't so easy. These days, it's sort of the opposite. We have really sophisticated instruments, but we're trying to measure very, very strange relationships that aren't necessarily obvious at first appearance. And so it takes a lot of work now in chemistry and in physics to try and take your data and try and fit them to a straight line. Or I should better say, try and fit a straight line to your data. That would be a better way to say that. I remember my graduate school apartment mate was sitting one day and he had this really complicated data set and he was trying to figure out a curve that would fit that data. And he said something like, why was I born after all the simple, important linear relationships were discovered? Okay? So he was hoping that he'd just get his data and would show up like that. But anyway, he was not able to do that. So chemists like these nice straight lines. As I said, this kind of data is perfect, but sometimes we don't have such simple lines. Sometimes we have a little more complicated relationships. Here I actually show you what the relationships are. This again gathered by my students in the Chem 110 lab 2 weeks ago. So we have real live data here. And you might recognize this again if you remember your chemistry class or physics class. It's pressure versus volume. Okay. Or you might be able to look at that line there and decide, what's the relationship for those data points. Okay. Straight line, curve, okay. Inverse relationship. Okay. Some of my students in lab really thought that was a linear relationship. But when you put the line in there, you can realize that it isn't a very good fit there when you fit a straight line there. So then the question is, how do you figure out, how do you take that data, how do you manipulate it, how do you get it to be in a slope-intercept form? Okay? And so one thing you could do in the past is you can take that data and you can try and draw the best fit to that. In the old days, you would use something like this. Anyone recognize what that is? Okay. John does. Anyone else? I borrowed this from John. We were laughing because both our fathers were engineers, and we both used to play with these as children, not knowing what they were and just drawing silly things. It's called a French curve. They used to come, I think the full set, it says, was 28. I don't remember my father having all 28, and I probably broke half of them just playing around with them. But they were used to fit data or fit lines and then draw a nice smooth curve. And if you did the right combination of all 28 or a few of them, you could actually draw a smooth line through different points. So architects use them, engineers use them. I don't remember if mathematicians used them, but maybe they did. Now I looked on the Wikipedia website about French curves, and it said that some of these were specifically made to fit parabolas, and others were made to fit hyperbolas. But I looked further into that, and there wasn't any supporting evidence. So I don't know if that's actually true or not. Maybe a future talk for the mathematics seminar. Someone can do a study on French curves and see if they really were that. Right? So think about that. Right? But the nice thing about French curves is it gets you a line there, so you can see a nice curve that goes through all your points or most of your points. But the trouble is it doesn't tell you what's the equation for that line. You still have to work on that yourself. So then you have to sit there and figure out, well, how am I going to figure out how to get that into a linear form? Okay? Anyone have an idea of what they might want to try manipulating the data?
Say linear form or closed form?
I'd like to get the y equals mx plus b.
Linear regression.
What's that?
A linear regression.
Oh, well.
But you want it to be a curve, right?
I want it to be a line.
Oh.
Okay, so I want to get that to be a straight line. So my goal on all of these, I want a straight line. Okay. So what, because we can always, well, let's put that. So I want to go for a straight line. So what I can do here then is do what Boyle did, okay? And this is Boyles Law. It's pressure times volume is a constant, okay? And so he discovered it was an inverse relationship, that the pressure and the volume equal a constant, which means the pressure is inversely proportional to the volume, okay? And so we have what's called Boyles Law then. You have your nice straight line there, okay? Relationship, so we can have this y equals mx plus b form, okay? Now, I'd like to do demonstrations, and I don't get too many chances to do demonstrations in math talks, but I'm going to do a demonstration here to show you Boyle's Law. Okay? So I have a cup, and I have this nice little lid. Okay? I don't know if you've seen these yet. They're made out of silicone. The bottom's nice and smooth, so it's just a floppy rubber lid. But you're supposed to put it on your food so your food doesn't rot when you put it in the refrigerator, or so you don't get smells in there. Okay? So it's a nice lid, very smooth. I can put it on the cup. I can slide it off the cup. But if I put it on the cup and I lift, the cup stays there. Okay? So the question is, why does that do that? Okay? This is not sticky, okay? So it has nothing to do with being sticky. But why can I hold the cup up that way? Okay? What's that? Oh, very good. It's creating a partial vacuum. Because what happens when I lift up on this is there is a trapped sample of gas inside that cup. Okay? When I lift up on the lid just a little bit, the volume inside that cup gets a little bit bigger. And if the volume gets bigger, what happens is the pressure, according to Boyle's Law? Well, remember, that's a 1/over relationship. So if the volume goes up, the pressure has to go down. And so if I lift on this, the pressure inside that cup is now lower, at least a little bit, than the pressure on the outside. And it's just enough that now there's more pressure on the outside than the inside. And so what's really happening is air pressure is pushing on this cup and forcing it up into the lid, and air pressure is pushing on the lid and forcing it down onto the cup. And so it's held together by the fact that there's higher pressure on the outside than on the inside. How do I get the lid off? I just have to lift up the edge and let the pressure equalize, and then it comes apart. Okay? It works really well on tabletops even. This is even harder to get off. I just put it on the tabletop, so I just dropped it there. If I try and pick this up, I can pull on this all day long, and I am not going to get that off of there because it lifts up just a little bit, and I have 15 pounds per square inch air pressure pushing down in there, roughly, and so I cannot get that thing off of there. So how do I get it off? I just slide it off, and it comes off, because then I'm not trying to pull against the pressure of the air. Okay? So that's my little demonstration of Boyle's Law. Okay? So let's see. What do we want to go to next? The next one is where I think chemists made a mistake, but I have to live with it because I have to teach chemistry. And this is a question of, is a solution acidic or basic? Okay? And specifically, we want to look at an equation. If you had hydrogen chloride and water, what's going to happen when you put hydrogen chloride in water? You're going to make an acidic solution or a basic solution. What's going to happen? And there's the reaction that occurs. And when the reaction occurs, this is really what we're interested in, the H3O+. It's called the hydronium ion. That's actually what's the acid in water. When you make a solution that's acidic, you're really worried about H3O+. You get the chloride ion too. We're not so worried about that. We're worried about the H3O+. So we want to know, if I put a certain amount of hydrogen chloride into water, how much H3O+ am I going to get? Because that'll tell me how acidic it is. Okay? And we have a device for measuring that. There's a, I guess it's an apparatus called a glass electrode. And it can directly measure the relationship between the amount of H3O+ in water. And it actually measures the voltage. Okay? And so using that, we can actually figure out what's the relationship between how much HCl I put in water and how much H3O+ actually forms. And if you look at that relationship, I sort of cheated again and I showed you. It's a nice straight line. We have this linear relationship. And if to two significant digits, and I mentioned that I think next December's talk's on significant digits. So here's a shameless plug for December's talk already, math seminar. It's on significant digits. To two significant digits, however much HCl I put in there, that's how much H3O+ I'm going to get. Okay? So it's perfect linear relationship. These are all written to two significant digits. And I get my nice line. Okay? So I think we should have just stayed with this, because if you told me how much HCl I put in there, I could tell you, well, that's how much H3O+ I'm going to have, and I can use that to tell you how acidic the solution is. But the chemists didn't want to do that. Maybe it's because we had these tiny numbers. Maybe they were afraid of all these zeros. Maybe they were afraid of the powers of 10. That last number down there is 1.0 times 10 to the negative 15th. Gets a little big to write down, but we could have written it in scientific notation. But what did they do? Well, if you have lots of 10s, how do you get rid of lots of 10s? Anyone? Logs. Okay, so we can do it in logs. Okay, so we took logs of all these, and that was okay. Took a lot of logs, so that would make the number smaller, except for the fact that these were numbers that were less than 1. So then when you took the log, you have to have the negative of the log, and you will get what you were usually used to saying, which is that we have this term called the pH, which is equal to the negative log of the H3O+ concentration. Right? Except then when you plot that, you no longer are talking about y equals mx plus b. You now have a logarithmic function, okay, an exponential function. And now it's the bane of my existence when I teach pH, because most people don't understand logs, and they forget that there's a negative term in there. Okay? And so first of all, they think that a pH of 7 is more acidic than a pH of 1, because we're talking about pH, and they wonder why 7 is greater than or is less than 1, but that's because of the negative term. And then I have to convince them that if I have a pH of 7 and a pH of 1, that's not a difference of 6, it's a difference of 10 to the 6. So that's 1,000,000 times more strongest solution. So a solution with a pH of 7 is 1,000,000 times less acidic than a solution with a pH of 1. Okay? You don't know how hard this is to teach general chemistry students. And I would much prefer to have that back in that nice linear relationship that let's just talk about H3O+ concentration. So what they did with the glass electrode is they just fancied up the name and called it a pH electrode, and now you change the voltage, so your meter's not reading voltage, it just reads pH units, and you now have a pH meter. Okay? So I think that's a big mistake, but I have to live with it. Okay? Let's see. Let's try something else near and dear to the heart of chemists, and this has to do with measuring equilibrium constants. Okay? And these are important to chemists because they tell us how far a reaction has gone. It's called the extent of a reaction. We want to know how much product formed. And the equilibrium constant is a ratio of how much product you have compared to how much reactants still remain. And it's a really important number in terms of deciding, is this reaction going to give us a lot of product, or if I let it react, will it just stay mainly reactants? And so we are interested in that number to tell us what's the extent of this reaction. It's often a term they use. And then when we do that, we want to know, how does it vary? How does the value of the equilibrium constant K vary as the temperature varies? Because that'll be another important aspect of this reaction. So we got to be careful with our K's here. This is a capital K. The capital K is the equilibrium constant. I'm going to measure my temperature, but it's going to be in Kelvin, so I spelled Kelvin out just so you wouldn't get it mixed up with the K there because they're all capital Ks. Okay. So there's our relationship between the equilibrium constant and temperature. And so when chemists first looked at this, they have to look at that curve and they have to decide, can I get that to be straight? Can I get that into the y equals mx plus b form? Okay. And the question is, well, how do you know how to do that? Okay. What allows you to take that information, that data that you measure, and then turn it into a nice straight line and get it into the slope-intercept form? And I took a quote out of a book I just read by Ian Stewart, good mathematician, writes really good books. And he said, it's often difficult to reconstruct how the mathematicians of the past arrived at new discoveries because they had a habit of presenting only the final outcome of their deliberations, not the many false steps they took along the way. Okay? And I think this holds true for chemists too. We don't always see what work they did to get there, but then we see the final result. So I'll show you the final result here. Might help. So first we have a famous thermodynamic equation in chemistry, delta G naught equals negative RT ln of K. Okay, what does that mean? It means the delta G naught is the change in Gibbs free energy at standard state. R is the thermodynamic constant. You may know it as the gas constant. It's the same number, just in different units, so the value changes slightly. There's our temperature, and there's our equilibrium constant. And you might think, oh, that's great. There's an equation right there. I can just rearrange that equation, and I can relate T to K, my temperature to my equilibrium constant. But the trouble is delta G naught also changes as you change the temperature. So we'll have K that varies as we change the temperature, and we'll have delta G naught that changes value as we change the temperature. So that one equation isn't going to really get us where we need to go. So then there's another equation that we can bring in, another famous equation for thermodynamics. Delta G naught equals delta H naught minus T delta S naught. Okay? What does that mean? Well, there's our change in free energy, or Gibbs free energy at standard state. Delta H is the change in enthalpy, or heat, at constant pressure at standard state. And delta S is the change in entropy, or randomness, okay, at standard state. So now we have these two equations. What can we do? Oh, actually, one other point. Delta H and delta S naught can both be considered constants if we don't change our temperature too much. So what could we do to maybe get a line out of all this stuff? And remember our curve we had before. So we have two equations here. Okay? So what did the chemists do? We want to relate K and T. Bruce, you're going to tell me. Throw them together, because they're both equal to delta G naught, right? So we throw them together. Negative RT ln of K equals delta H minus T delta S. Okay, so now you're in math class. What do? Remember, we're going to vary T, and we want to see what happens to K. So we're in control of the temperature, and we want to see what happens to K. What next? What's that? You can tell me. This is good. Solve for K. Okay, so how do I get K all by itself? Yep, divide by RT. Okay, so you can rearrange that, divide by RT. Okay, so we take the negative over 2, so we divide by negative RT. Okay, so there's our negative RT. The T goes away here, right, because it was T delta S, and I divided by RT, so that goes away. I don't know if you see it there. There's our y, ln of K. Our x is hiding in here. Where's the x? The x is the 1 over t. So if I pull it out that way and show it in that form, it might be a little easier. There's our y. There's our slope, x, b. Okay. So then if we take that same data that we had before that gave us that curve, and we plot it in that form, you get a nice straight line. Okay. And now what do we have? We have all sorts of great information out of this. We can get delta H from our slope. We can get delta S from our y-intercept. And if you remember back, we had that delta G term. Now we can pick any temperature we want and solve for delta G, okay, because we know what delta H and delta S are. So we can go back and get delta G. Okay. So again, we showed students this in general chemistry, and we don't tell them all the hard work that went into it. But somebody somewhere had to do a lot of thinking to try and realize that they could relate those two different equations and put them together to get this nice equation that gives us a nice straight line. Okay? And again, chemists like those straight lines. One thing we do like about them is you can kind of eyeball those things and decide, is that a good fit or not, the goodness of the fit. I read one thing where they call it chi by eye. Okay? If it's in a straight line, you can look at it. Chi meaning the chi squared. It's a statistical analysis to see how the goodness of your fit. Okay? So chi by eye means I'm just going to look at that and say, is that going through all those points? Is that really a straight line? And it turns out with straight lines, at least in my opinion or in my experience, you can sort of tell if they are lying on a straight line, whereas if it's a curve, it's a little bit harder to see if those data points are falling on some kind of curve that's either an exponential or inverse or something like that. So that chi by I test is pretty straightforward with a linear function. Okay. Let's see. Another famous plot of data shows up all over the place in physics and chemistry. Okay. So I've again left off the axes labels because I think if I put them on there right away, everyone would recognize it. Okay. Anyone know what kind of relationship I have between x and y? Somehow the people who originally gathered this data look at that and said, I know what that is. That's an inverse relationship. That's an inverse relationship. If I put the axes on there and label it, it's potential energy versus the distance between the particles. Anyone know where that shows up in the world of science, physics? What's that? The periodic table? It could show up in the periodic table. Where in the periodic table? I don't mean to put you on the spot, so you don't have to. Well, I was thinking sort of a bigger picture other than that, although it can show up between atoms. So this works for how positive charges interact with negative charges. Okay, it's the force of attraction. I was going to focus more on something that was a little more common, I guess, in everyday life, and that would be gravity. Okay? So this is a curve of the potential energy due to the attraction of gravity. Okay? In that, if we do a plot of the mass of the one object compared to the mass, or multiplied by the mass of another object, that's the universal gravitational constant, and we divide it by the distance between the masses, we'll get the potential energy. There's a negative sign there. That negative sign is really important. That tells us that as the particles get closer together, their potential energy drops. Okay? Some people get upset about this because we tend to plot these as this is getting more and more negative, which means our potential energy is getting lower and lower and lower. And as we get farther and farther up, that means that that's getting closer and closer to zero. Okay? That sometimes bothers people, that at infinity, your potential energy is zero. Okay? But that's high compared to what's your potential energy when they're getting closer together. Because when they're closer together, what's your potential energy going to be? So here we're getting closer and closer together, but we're getting more and more negative. What should our potential energy be when these two things are almost touching or touching? Negative infinity. Okay? So you can move that around if you don't like that, but we have the ability to actually make that scale whatever you want. But essentially, the potential is going to be negative infinity if you get them touching each other. Okay? But we tend to not think of it that way. We tend to think of potential energy as if I'm standing on the Earth, what's my potential energy relative to the Earth? Zero. So we just kind of move our scale up. Okay? So we make zero be way down there and then just move our scale up and make that be like a really, really big number. Okay? But that is definitely an inverse relationship. Potential energy is related to 1 over the distance between the masses. Okay? Somewhere in my past, I took a physics class. And in that physics class, I learned that the potential energy of some object when I picked it up was equal to mgh. Did anyone learn that equation recently? Okay. So this didn't bother me at the time because I was just trying to get through my physics class. But if I look at it now, what kind of relationship is that between potential energy and distance? Potential energy equals mass times the gravity, acceleration due to gravity at the Earth's surface times the height. What kind of relationship is that between distance and potential energy? Okay. It's a nice straight line. It's a linear relationship. How can I have a linear relationship? Okay. I just told you that that relationship between potential energy and distance was an inverse relationship. Okay. So now this bothers me, okay, because somebody told me that potential energy is mgh, and yet if I look into it more, the potential energy has to be related to the 1 over the distance. So where does that sort of disconnect come from? Okay. Well, again, here's our actual equation that has to do with the equation of what's the potential energy. It's related to the product of my masses and the constant divided by the distance between the masses. And somehow we have to make that sort of go along with this equation up here where the potential energy is just mass times a constant times height. Okay? And so to do that, you actually need to understand that they're not really asking you to calculate the potential energy. They're actually asking you to calculate the difference in potential energy. It's really hard to calculate an absolute potential energy, if not impossible to calculate an absolute potential energy. You want to know what the difference is. Where are you now compared to where were you before? That we can figure out. Okay? So that means when we're doing mgh, we're really doing mg delta h. What my mass and my gravitational constant, in this case the acceleration due to gravity, stay the same. It's the heights that change, and that'll get me a difference in potential energy. So now I can go back and grab that other equation, okay, and plug in my values here. So here's my final height. Okay? And if I'm going to do this to the Earth, then we have to see what these terms are here. That's the gravitational constant. That's the mass of the Earth. That's the mass of whatever I have. Let's say I'm going to pick up this cup. Okay? It's not very heavy, but it'll be attracted by the mass of the Earth. This is the radius of the Earth squared. Does anyone know why? Or radius, sorry, that's the radius of the Earth. Why do we use the radius of the Earth when we're doing this? Anyone know what that assumption is?
The distance from the Earth to the center of the Earth.
That's right. So why are we going to the distance from the top of the Earth to the center of the Earth?
That would be your total distance from the center.
Yeah, so what's at the center of the Earth? Yeah, all the mass. Okay, the mass of the Earth when you do this problem is assumed to be right in the center. Okay, my wife then asked me a question: what if I drilled a hole all the way through the Earth and dropped something? What would happen when it got right to the middle? Would it float? I don't know. That's why. How do we do this? I mean, this is the question, right? Because that's the assumption that all the mass is there, but all the mass isn't really there. But what happened? Would it float sitting right in the middle of the Earth? Yeah, good question, isn't it? Okay, so. We use the radius of the Earth as the distance between, as distance between the object and the center of mass of the Earth. Okay? So here's my final state. I have the radius of the Earth, and then I lift my cup up, say 1 meter off the Earth. Then my original state was all the same terms, but now it's the radius of the Earth. That was where I started out initially. So I pull out my common terms, and then here's what's left. Okay? So what am I going to do to make this simplified? Nice simple math here. What do I have to do to combine those two fractions there? A little bit of math here. Common denominator, cross multiply, whatever you want to do. And so I'll get this equation. Okay. So I did the cross multiplication and added them together and put them together with common denominator. So it's the radius of the Earth minus the height minus the radius of the Earth, which is nice because that just gets me the negative of the height. And down at the bottom, I have the radius of the Earth times the radius of the Earth plus the height. Well, here's where we have to make an assumption. What do I have here? I have the radius of the Earth squared plus the radius of the Earth times the height that I've lifted the cup off the Earth. Okay? So the Earth is about 6 times 10 to the 6th meters in terms of radius. What's that? Well, volume would be 3 dimensions. I only have 2 here, right? But that's a good guess there. But that's still 2 dimensions, and so is that. But this is about 4 times 10 to the 12th. And this right here is still the radius of the Earth times 1 meter that I lifted my cup up off the surface of the Earth. Okay? I would submit to you that that term right there is pretty small compared to that term, because that's the radius of the Earth squared, and that's just the radius of the Earth and the cup being 1 meter off the Earth. And so we're going to cheat here and assume that that is insignificant compared to that. Okay? So what happens if we consider that insignificant compared to that is we just ignore that. And if we ignore that, we just have r squared on the bottom. And if we have r squared on the bottom, we get the change in potential energy when I pick the cup off the Earth as being, so here's my gravitational constant, the mass of the Earth, the mass of the cup or whatever I pick up. The radius of the Earth squared is on the bottom. There's my height. Notice the 2 negatives cancel out, that one and that one. And if I admit that the gravitational constant times the mass of the Earth divided by the radius of the Earth squared is g, that's where we get g from, then this whole thing does collapse down into mass times the acceleration due to gravity times the height that you lifted the cup off the ground, and it ends up being a nice linear relationship. Okay? So on that curve, what are we doing? We're just talking about one little teeny tiny section of that curve. Okay? Because we're not letting the height get too big, we're not getting too far away from the Earth. And if we do that, you can pretty much find a straight line in any curve if you keep the part that you're looking at small enough. And so we're still on this curve, we're just taking little tiny sections of it and saying that's the part we're interested in. Small distance away from the surface of the Earth so we can get a straight line out of it. So it is still that same curve there. It's an inverse relationship, but we're just taking a small section. Right? Makes life a lot easier. This is like all your other physics problems where they say, like, ignoring friction, do this. Ignoring wind resistance, do that. Okay? Ignoring this other term, do this. It makes your life easier when you're trying to do these calculations. Okay? Now, the last set of all the examples I'm going to give have to do with kinetics. Okay? And this is where Mr. Arrhenius, remember him, the guy on here? This is where Mr. Arrhenius comes in, because he was a kineticist. So this is a study of reaction rates. How fast does a chemical reaction go? Okay? Another important aspect of chemistry, from anything having to do with how often should you take a dosage of medicine to how long does it take for a chemical reaction to occur so we know when to add more reactants. And so we want to know then, when we start with a concentration of a reactants, how is that going to affect how fast this reaction goes? Okay? And so I'm just going to take a very, very simple example of a chemical reaction. In this case, sorry about all the chemistry here, but it is a chemistry talk about the use of math, right? So I have two molecules A, B, and I'm going to let them react and make molecule A2 and molecule B2. Okay? So it's a nice, simple chemical reaction to use as an example here. If we do that in solution, very likely it's going to occur by one of two processes or mechanisms. Either one of those molecules, AB, is going to fall apart on its own. If you have enough thermal energy, the bond will break. It'll break apart into two different atoms. And a whole bunch of them can do it all at once, but they don't need to run into anything else or have anything else make them fall apart. They'll just fall apart on their own. That's called a unimolecular process. Why unimolecular? There's only one molecule, and it falls apart, so it's a unimolecular process. The other most likely thing to happen, if it isn't a unimolecular process, is that you have two pairs of AB molecules running into each other. Okay? And so then they're going to collide, and they're either going to make intermediates or they're going to make the final products. That would be like A2 and B2 there. Okay? So we're not really interested in what happens on the back end of this, what the products are. We're now interested in what's going on with these reactants. Do I have to have one molecule that falls apart, or do I have two molecules that have to run into each other and then cause that process to occur? That's called a bimolecular process. So again, it gets more complicated. There are termolecular processes with three particles running into each other. There are some reactions that don't depend on the concentration at all, but we're going to focus on these two. Okay? So often what happens then is you, the chemist, would do an experiment. So we'll just talk about, here's our reaction again, and you can measure the concentration of AB, and I'm going to use the units of moles per liter, and we measure how long it takes in time per second for that concentration to fall off. Because AB is a reactant, and I want to see how quickly does it go away as the reaction occurs. Okay? And then the question again is, I look at that as a chemist, and I want to know, okay, was this a unimolecular reaction or a bimolecular reaction? Because those are the two most likely things for it to happen. So those are the two easy things to check for first. Okay? So to do that, chemists, once again, decide we want to take that data right there and we want to turn it into a straight line. We want to get it into y equals mx plus b. If we do that, we can get something out of there called the rate constant. It makes our lives easier to explain that reaction more thoroughly. So we set about trying to figure that out. So you look at that, and again, if you're getting used to these, I've given you a lot of inverse relationships and some exponential relationships. And just with the practice eye, you look at that. If you're first starting off and you're trying to decide, well, how am I going to straighten that thing out? Okay? What's the line for that? And I'll give you some information that will help. Okay? So for that reaction, the rate of the reaction is equal to the decrease in the concentration of AB per change in time. We'll go backwards there. Okay? So the rate would just be the change in the concentration of AB per change in time. What's happening to AB? Is it getting increasing in concentration or decreasing? It's decreasing as we go along, right? It's dropping. So that means when we go back to this slide, when I write that down, I'm just going to say the rate of the reaction is negative because it's going down. My deltas are my changes, right? And this is chemistry shorthand for concentration. You use square brackets, makes your life easier. So that's just the change in concentration of AB per change in time. Okay? All you mathematicians here ought to be thinking of a way to solve this right off the bat now, because I have little deltas there. When I see little deltas, that maybe makes something pop into your mind. Okay? So then as a chemist, you decide, all right, I need something else to help me figure this out. So if that reaction, I'll just make a supposition. If that reaction involves only one molecule of AB, then this has to be a unimolecular process. And if that's true, then the rate of the reaction equals K times the concentration of AB. Okay? So I'm going to have two ways to describe the rate of the reaction. The fact that it's the decrease in the concentration of AB per change in time, but also that it's equal to this K, this is our rate constant that we're interested in, times the concentration of AB. Okay? So once again, what do I do to make my life easier here? I'm going to get my straight line out of here by setting those two things equal because they both equal the rate of the reaction. And if I do that, I get that equation. Okay. Negative delta AB over delta T equals K times AB. Okay. What should I do next? That's the question. Now it's all set for you to solve mathematically. Okay.
Integrate both sides.
Oh, integrate both sides. That's right. So I'm going to rearrange. So we can get a line out of this. So I'm rearranging. I'm getting AB over there in the bottom, and I want to integrate both sides. Okay. So if I'm going to integrate both sides, there's the AB there, but if I call it x for a little bit, that would be 1x dx, 1 over x dx. Okay. What's the integral of 1 over x dx? All you calculus people there. What's that? It is the natural log, that's right. So the right side's easy. You're just integrating k dt, and k is a constant. The left side, you had to remember the integral of 1 over x dx is the natural log of x. So I have the natural log of AB at time t, its concentration at time t. I subtract from that the natural log of the concentration of AB at time 0. Time 0 is 0 over here, so I only have the negative kt term on this side. Okay. All right, let's see. Now I need to get this into y equals mx plus b. Where are my constants here? Well, k is a constant, but which one on this side is the constant term? 0, because that's what I started with. Okay, so that's going to be my constant term. So this is the one that's going to vary. The concentration of AB is going to vary with time. Okay, so that I want to keep as my y. So then I can rearrange it. I don't know why I went green here. I just thought, oh, it's green. We're there. We've made it. Okay, so the natural log of the concentration of AB at times t is equal to negative kt plus the natural log of AB at time 0. Okay, so there's my y equals mx plus b. Okay. So if we plot that, we get a nice graph. The slope's equal to the negative value of the rate constant k. For a first order reaction, this rate constant can be then used to find out what's called like the half-life of the reaction. So you may have heard of that with like radioactive decay. Radioactive decay is a first order process, and so you want to know what the half-life is. How long does it take for half of the sample to decay? You can get that from that k right there. That's not the half-life, but that's the rate constant you use to calculate the half-life. Okay? Another talk, but not this talk, another talk. Okay? So for that reaction, we discovered that was a unimolecular reaction because when we plotted natural log of AB, concentration AB, versus time in seconds, we got a straight line. We get it into the slope-intercept formula. What if we do another reaction? Okay? It happens to have the same form, 2xy going to x2 plus y2. I just changed the variables, or I shouldn't say the variables. I changed the name, the identity of the compound so you can see the difference. So here again is a plot of the concentration of xy in moles per liter versus time in seconds. So again, I'm measuring the experiment. So the experiment is occurring and I'm watching xy disappear. Okay? And then the question is, well, is that reaction going by the same mechanism that the AB reaction did? Okay? And just so you can compare, there's our AB reaction. So there's the data from the AB. I tried to get them to line up nicely with the time. The concentrations were slightly different. But are those two doing the same thing? Remember, this is AB. That was a exponential decay. Is that an exponential decay also? I mean, that's what you want to know. Well, I see someone shaking their head. You're like, no, that can't be. It looks different. Well, there's an easy way to check. If you're the chemist, you just say, well, my first shot is if that's actually first order, all I have to do is plot the natural log of the concentration versus time and see if it's a straight line. And if I do that, okay, here's the chi by I test. Okay, is that a straight line? Not quite. I mean, if you look at it, there's a bend to that thing. It's not a straight line. I forgot if I put a straight line in there or not. I didn't, but if I were doing this, I'd look at that and think that's not quite a straight line, so I'll try my other option. My other option is if it's not first order, it's very likely then the second order reaction. So now I have to figure out, well, what do I have to do to my data to get my second order reaction to get into the y equals mx plus b form? So here we go again. Rate of reaction. Same thing as we had before. We're losing xy over time. And then now we have one more thing to add here. If it's a second order reaction, or a bimolecular process, I should say, then our rate of reaction is equal to the rate constant times the concentration of xy squared. So here's where the difference occurs. Before it was just the concentration of our substance to the first power. Now it's the concentration of our substance to the second power. So we have to go through and do our math again. We set those two equal. Okay. almost the same as before, but now that's squared. That just makes our calculus a little more interesting, okay? Because we can get a line out of that. Okay? So delta xy over xy squared equals negative k delta t. Again, we'll integrate. Okay. What's the integral of 1 over x squared dx? You don't have to say it out loud, but you're thinking, you know what it is, right? So if we do that, I plugged in my numbers. I get 1 over x, negative 1 over x. So this is negative 1 over x, and then I'm subtracting. That's my top limit, my bottom limit. So I'm subtracting negative 1 over xy, which gives me a positive there. Okay, everyone catch that one? Want to make sure. And then I just have negative kt over here. And this is going to be my constant right there, because it's at time 0. That's my variable, so I want that one to be y as I vary my time. And so if I rearrange it, I can then see that if I plot 1 over my concentration of xy at any given time, I will get this in this y equals mx plus b form. So as time changes, I have to plot it against 1 over the concentration. And I get a nice straight line again. Okay. And the slope now is the value of the rate constant. So here's this direct relationship. Whatever the slope is, that's our rate constant. So again, as a chemist, what you would do very quickly are these 2 quick tests. After you get your experimental data, you can plot the natural log of the concentration versus time, and then you can plot 1 over the concentration versus time. And whichever one gives you the straight line, you'll know, oh, that's a unimolecular reaction or it's a bimolecular reaction. If it's neither one of those, now you have more work to do. But in real life, that takes you, minutes to do that. And so it's a fast way to figure out what kind of reaction you have there. Okay? So this work was done by Arrhenius. And another thing that Arrhenius carried out, the Svante Arrhenius, our first guess on what's my line, is Arrhenius also worked on how does the value of that rate constant, k, change when you change the temperature. So now we have another k here. I was once in a graduate school class where there were 4 k's in the equation, and the guy could not write worth beans, and so no one could ever tell which k he was talking about with the 4 k's. But here I have another k. It's a little k, so the rate constant k is a lowercase k. Again, here's Kelvin, the temperature. It's a big k, but I wrote the word out, so we didn't get it mixed up here. Okay. Arrhenius wanted to figure out how does the rate constant change as you change the temperature. So if you look at it, you can sort of see what's going on here. What's happening to k as the temperature goes up, this little rate constant? As the temperature goes up, k is getting bigger, but we want to figure out what's that relationship. And I have a slightly different purpose to prove here, and I'm sort of running out of time. And that is, so I'm just going to show you what Arrhenius figured out. Okay. Anyone know what kind of curve that might be? Want to take a wild guess? What's that? Inverse, exponential, parabolic. I know it looks a lot like a parabola, doesn't it? Okay. It's actually exponential. Okay. This is called the Arrhenius equation. So this is why I asked John to put Arrhenius' picture on the advertisement, because he did all this kinetics work. And that's called the Arrhenius equation. Okay. And it shows us the rate constant is actually equal to a constant which is called the collision frequency factor. Okay. It's related to how many molecules are running into each other and how efficient they are. And then we're going to raise e to the power of e sub a. That's the activation energy, okay, which is how much energy do you need to get the reaction going. Okay, it's the reason why we're happy about activation energies. It's the reason why reactions just don't take off right away. So I'll make an astounding statement and then not back it up. But this piece of paper is on fire right now. It's just burning really slowly. Okay. So thermodynamically, I have a room full of that has oxygen in it, and I have carbohydrates. This is the fuel, and so the oxygen is reacting with the fuel. And remember my delta G naught equals delta H naught minus T delta S naught equation? That equation tells me that this piece of paper is on fire. Okay? It's just that we have activation energies, and the activation energy, luckily for us, is high enough that in this room, at this temperature, this is not going really quickly. But it's still going, and you know that if you leave a bunch of paper sitting around for long enough, what happens to your paper? Think of newspapers stored in the garage. Okay. Yeah, it turns yellow, it's burning, and that's oxidation, which is a name for slow burn, right, or fast burn. Okay. And you all, there is a book that is written, that's title tells you what temperature you have to get paper to get it to go spontaneously. Fahrenheit 451. Okay, that's at that temperature, you've gotten the molecules moving fast enough that now you've overcome that activation energy, and now those bonds will start automatically breaking, and you'll get oxygen to react with the paper. Isn't this scary? Okay? So it's on fire. It's just going slow. Okay? So we're happy about activation energies, and we want to do these calculations because we want to find out what the activation energy is. It's nice to know that. Okay? It's like in this room, too, there are hydrogen molecules and there are oxygen molecules. If there weren't activation energies, we'd have little explosions occurring all over the place. But they don't, because that's really high for oxygen and hydrogen. There's our constant again, R. That's the thermodynamic constant. So that's the Arrhenius equation. Again, we're not going to go through all the stuff that Arrhenius had to figure out how to straighten this thing out. But once you see the equation, you can do a little math. And I'm going to skip the math and just show you what he came up with. Okay? He rearranged it. Took the natural log, that would make sense, right? So the natural log of k, that will be our y. Negative EA over r, that's our slope, and it's got our activation energy in there, a very important number. There's our x value, 1 over t, and then we get the natural log of the collision frequency factor as our y-intercept. So when we plot that, we get a nice straight line. I actually put the numbers down here because I'm going to need these in a moment to show you what's going on here. Okay? So our activation energy, it's a pretty big number, and that's in, got to make sure I get through, that's in joules, okay? But it's also divided by R, but we won't get into too much details there because then I'm going to have to teach you a lot of chemistry. But again, we have a large value, which is nice and, for this reaction, which means it has a high activation energy. 31.30, that's the natural log of A. So that means that A is a big, big number or a little tiny number? A is a pretty big number, okay? So think of molecules, they're tiny, lots of them are colliding all at once. So we're going to get a big number when we do that. Okay? If you want to plot it or present it in the way that Arrhenius actually usually presents the Arrhenius equation, then you can see that A is 3.9 times 10 to the 13th, okay? So I just brought A out front, and then, so that's just the natural log of A is 31.30, and then there's our activation energy again. Now, I'm showing you all these numbers here finally because I want to show you that, in fact, the sort of art of drawing straight lines in chemistry is no longer as necessary as it used to be. The age of trying to work to straighten out these lines is coming to an end because we have the here and now, which says that we have all sorts of nonlinear fitting programs that exist all over the place. Excel has them, Mathematica has them. The ones we use in our lab, it's Logger Pro, Vernier Incorporated uses them. Do you guys use Vernier probes in math at all? No. Company out in Oregon, they make all sorts of measuring devices. But they can do all the work for you. You don't have to do this anymore. You can just use the nonlinear curve fitting programs to do this. So let's see, I got to get to my kinetics data here. So this is the same. I need my mouse here. There. Okay. Please work. No, I'm ready for that one. Almost an uh-oh. There we go. Okay. So this is the same graph of the same data that you saw before. I just put it on the Logger Pro. So there are all our points. Okay. So temperature in Kelvin, that's the rate constant. So what you do now is you gather your data, and then you look at that and you say, I want to fit that to a curve. And you just use your mouse, and you move up to the little program up there that says curve fit, and you push a button, and it gives you all sorts of choices. And this is a prepackaged canned program. I'm sorry that's small, but it shows up pretty big on the screen. It gives me all sorts of choices. Do I think that's a linear? Is that y equals mx plus b? Well, I could try it because it lets me try the fit. So I could say, I want that to be, I think it's y equals mx plus b. So I could choose that, and I could ask it to try the fit. And nah, that's not a very good fit. All right? So it's telling me that if that were the fit I chose, there would be my slope and my y-intercept. Okay? But then it gives you many, many choices here, one of which, and you can define your own also if you want, but one of the choices is this one right here. And now you got to think back to my previous slide. Okay? That's in the form of the Arrhenius equation there, right? Because I had the number a, actually it happens to be an a here. This is just the parameter that I have. And then an exponential of negative c over x plus b. That's the form of the Arrhenius equation. Okay? I have these parameters. The nice thing about this program is it will do a best guess, the first best guess. So it's not going to pick one, but if I ask it to try a fit, it's going to think about this and try and get its first best guess. And its first best guess isn't that great, okay? But if I have a little bit of knowledge about what equation I'm trying to fit, I can think, I'm pretty sure this is the right one. I just have to ask the computer to try it again. So now the computer did its first guess, and it used a certain set of parameters. And now if I ask it to guess again, it's going to try another set of parameters. Okay? So I can ask it to try another set of parameters. If you'll notice, these numbers are changing right here. A, B, and C are changing. So I'll try another fit. And it's going to, and if you notice, the line's getting a little closer. And if I try it again, then I can try it again. And the number is gradually approaching. We'll get there eventually. What is that now? 3.37 times 10 to the 13th? 3.72. I've hit the button a few times and nothing much is happening. It gets stuck right there. But does this number look familiar to you? 3.7 times 10 to the 13th? Okay, that's my value for A, which was in fact my value for A. And this number, 1.93 times 10 to the 4th. Okay, just to remind you, I'll go back to the PowerPoint. Let's see, I got to go there and then back one. Those are my values there, roughly 3.9. They had 3.7 times 10 to the 13th and 1.93 times 10 to the 4th. Okay? I can get a nice curve fit off of that program. I don't have to spend all my time trying to turn it into a straight line and do all that work to try and get it into the y equals mx plus b form. So now I think back to my graduate school apartment mate, and I think he was doubly cursed because he was born after all the nice linear relationships were discovered, but he was born before we had all these nice curve fitting programs. Okay? Although he's still actually active in science and probably gets to use them now all the time. But so after leading you through all those little equations, we still teach our students that in general chemistry, and we still show them how to do it. But they themselves, if they did research, would not do that anymore. They would use one of these very powerful nonlinear curve fitting programs to carry out that process and find those relationships. Okay? So just like we don't use French curves anymore, and just like What's My Line isn't on TV anymore because it lost its audience, the fine art of trying to straighten out your line, straighten out your data into a straight line has been lost too, although some of us still carry it on. Okay? I have one more thing to show you though, and that is there's one other person on this flyer that advertised my talk, and he would have been a perfect candidate for What's My Line, because he worked in sort of an obscure field, but did all sorts of wonderful things and could have walked around probably in public and nobody would have figured out who he was. Okay? And so he probably could have fooled our panel of semi-famous experts at the time. Does anyone know who this person is? He made it on the sheet, so he must be important in some way, shape, or form. Anyone? Everyone knows what Einstein looks like, but you put anyone else up there other than Einstein, and they don't know who it is. Okay?
Your great-grandfather.
It's not my great-grandfather, although I might be related to him somehow. He is from Germany, and all my relatives are from Germany. John, who is that? Carl Friedrich Gauss. Oh, even the mathematicians are like, oh, wait a minute. So he would have been a great contestant on What's My Line. I think he could have won, because he could have fooled him. So there you have it.
You're a chemist.
What's that?
You're a chemist.
I'm a chemist.
That was your line.
No, I remember that. I'm a chemist. He got it. You were Arlene Francis getting me, right? Do you remember Arlene Francis? You always got Kitty Carlisle?
I heard of the name.
Yeah.
Before my time, though.
These are all these semi-famous people who are on What's My Line. For those who are too young, go Google it, go to YouTube and look on YouTube. There's all sorts of people on there. Questions? Why is Gauss up there? Well, you wanted me to put pictures of people on there. No. Yeah. Well, Gauss did a lot of work with lines, if you want to put it that simply as that. You can fill them in with more details. John, why did Gauss do a lot of work with lines? What has he done? Yeah. So there are, as I was coming up with this topic, I kept coming into more things like, oh, I could have done a talk about that. Oh, I could have done a talk about that. So there's French curves. There's linear regression. How do you do regressions? There's so much to do about the curve fitting programs that you have and how you use them and the math that's involved and finding out how much error do you have and how good your fit. But I was already on work on this one specific one, so I thought, okay, those are talks for a future situation. So.
I was curious on the computer program you
Yeah?
There's like a RMSE value.
Let's see. Oh, wait, which one's that?
I forget.
The Logger Pro. Let's see. I got to quit this. I don't have my mouse, so I don't know how to do this.
Alt-tab.
Alt-tab. Thank you. Am I ignorant or what here? Alt. Now I got to find the tab button. There you go. On that equation?
SE, close to the bottom above the OK and cancel the RMSE.
Root mean square?
Oh, is that what that means?
Yeah. So I think that is essentially their idea of how good this fit is. So if we went back, we could see that that number was probably very large when we started, and now it's getting much, much smaller.
Oh, yeah.
Chemistry folks or physics for that matter, this is probably a two-part question. Does anyone use log paper either by hand or in some sort of situation where you enter the data?
Only every once in a while when I guess we're feeling a little like treating our students cruelly, just to show them, I mean, at some point that's about at the level of having them use a slide rule at this stage. I think we kind of look at it that way. Okay? I mean, it's nice to do it because you're showing this a relationship, but I sometimes get in trouble because I still make all my students do it at least one plot by hand, and people get mad at me for doing that.
I guess that was a follow-up question. Is there a pedagogical value to having students do that occasionally?
Yes, I think so. Because a lot of them, and for mine, I do a simple experiment where we just measure the temperature in Fahrenheit and the temperature in Celsius. Okay? And it's sort of a ridiculous thing to do, but it's actually good for students who've never had a science class before and have them plot it and find out the slope of the line is actually the way in which the value of y changes divided by the way the value in x changes, and that slope actually is the relationship in that case for the ratio of the Fahrenheit temperature to the Celsius temperature. So make it a little more clear to them what they're actually doing instead of just plugging into a computer and having it pop it out.
You sure that don't just confuse them?
It probably does confuse them, but I still think it's good for them in that case. I sit there and talk to them about it and say, what did you actually just do? Because otherwise it's just a number, you just grab a number off the computer screen like that and say, oh, here's a number and this is it. What is 9/5? When in that equation, it's 1.8 is that scale factor between degrees Fahrenheit and degrees Celsius. And so I think if they plot it, they might actually see that and realize what's really going on. Okay? Otherwise, it's just a number. You're welcome. Thank you for having me.